So here we're going to talk about the unit circle and the area of a triangle. So starting with the unit circle, what a unit circle is essentially a circle put with the center in origin and a radius of 1 unit, meaning that the edge of the circle hits 1 on the x-axis, 1 on the y-axis, -1 on the x-axis, and -1 on the y-axis. What this unit circle can be used for is to describe what cosine and sinus actually show. So for this example, we have a line here which goes through the unit circle starting from origin, has the angle theta, and we have a point here where the line intersects the circle. This point will then have the coordinates of cosine of theta and sine of theta. The same thing goes for this line down here, except this is negative theta because this line is opposite. This line will then of course have the coordinates cosine of negative theta and sine of negative theta. As you can see, the distance here from origin to over here is sine, which is why this coordinate is sine of theta. And this distance here from origin to the point N over here is cosine of theta, which is why the x is cosine of theta. And lastly, out here we have the tangents of theta, which is a line which goes from 1 on the x-axis all the way up until it intersects the line mentioned before. Now for how you would use sine, cosine, and tangents. First, you need to know how or what you need to use to find sine, cosine, and tangents. For sine, you simply divide the opposite side of an angle by the hypotenuse in the triangle. And for cosine, you use one of the adjacent sides of the angle divided by the hypotenuse. And for tangents, you use the opposite side of the angle divided by the adjacent side of the angle. Now, one thing that's important to note here is that these rules only work when using right-angled triangles. So in all of these examples, just imagine that they're all right-angled, that they have a right angle here, a right angle here, for example, and a right angle here. You cannot use this with an arbitrary triangle, only arbitrary right-angled triangles. So for some examples here, we have this triangle where we want to find out what the length of side x here is. We have this angle here, and we have this side, which is the hypotenuse. And to find out what the opposite side is, we simply put all the values into the formula. So sine of 63 degrees equals x divided by 20, because x is the opposite side and 20 is the hypotenuse. Then we isolate x, and we just calculate and get the result 17.8, which should be the length of x here. Now for an example of how to use cosine. In this triangle, which is a sketch, which is why it is quite inaccurate, we have this angle of 32, this adjacent side of 12, and the hypotenuse of x. Yeah, as you can see, it's a pretty bad sketch, but this is supposed to be the hypotenuse. Again, we simply just put our values into the formula, so cosine of 32 equals 12 divided by x. Then we isolate x, and we get the result of 14.2. Lastly, we have an example of how to use tangents. In this triangle, we're going to try and find out what the angle is by using the opposite side and the adjacent side, or opposite side here and adjacent side here, to our angle. Again, we simply put our values into the formula, so tangents of x equals to 15 divided by 4, meaning the tangents of x equals to 3.75. And to find out what the angle actually is, you want to use inverse tangents. This also goes for the other ones, where if you have the sides, you can find out what the angle is by using inverse tangents, or the inverse versions of the respective rules. And you can see here that from using the inverse tangents, we get the angle of 75.1 degrees right here. Now for some trigonometric identities. The trigonometric identities is what you notice when you look at this unit circle one more time. You'll notice that here cosine is equal to the adjacent side ON divided by the hypotenuse OP, which is equal to x, because we don't know what the distance from O to n is because it can be arbitrary, divided by 1, because we know the distance from O to P is 1. Meaning that cosine of this angle here, which is arbitrary, is equal to x. We can also see that sine of Pn, because Pn here is the opposite side, and O is divided by OP again, because OP is the hypotenuse, is also y equals or y divided by 1 equals y, because again we don't know how long the side Pn is, but we do know that it's in this circle and it's arbitrary, so we can say it equals to y. Now, using Pythagoras' theorem, we can see that y squared plus x squared must always equal to 1, because the hypotenuse will always be 1. This means that cosine squared and sine squared, or cosine squared plus sine squared, will also be equal to 1, because, as we proved, cosine is equal to x, and sine is equal to y on this triangle. This means that you can use cosine and sine as a kind of variable in a way in algebra. So for example, you can say that you have 3 cosine and 5 cosine that equals to 8 cosine. Same with sine. You have 3 sine minus 5 sine equal 2 sine. And one thing you can also do is, if you have 1 sine squared, it will be equal to 1 minus cosine squared. And this also goes the other way around. Same for cosine squared is equal to 1 minus sine squared. And then you can use these values to perform algebra with these extra properties of sine being equal to 1 minus cosine squared and cosine squared being equal to 1 minus sine squared, and so on. Now, for the area of a triangle, you probably already know the usual method of saying that the area of the triangle is the bottom line times the height of the triangle divided by 2. So for this triangle, for example, the area would be a half times AB, being this line, the bottom line, times CN, which is this line from top to the bottom, which is the height, or just a half times this line C times this line H. Now, you'll notice that sine of A down here will be equal to H divided by B, because B is the adjacent side and H is the opposite side. This means that H can be represented by B times the sinus of A here. This in turn then means that you can essentially calculate the area using only a half times the bottom line times sine to whatever angle you're using times B, like in this example here. So to make it to simplify it a bit, the area of a triangle is equal to a half times the 2 adjacent sides to each other, and times the sinus of whatever angle is in between those 2 sides. So, for an example of how you would use it, a triangle has been drawn here. You have one line here which is 15 units long, and a line here which is 19 units long, and in between you have an angle of 35 degrees. All you need to do is simply put in everything into your formula. So we say that this line here is A, this line here is B, and this angle here is just sinus of whatever angle it is. So you get 15 times 19 times sinus of 35 degrees times a half equals 81.7 square units, or whatever this triangle is.